Hi everyone! Today we're going to wrap up Chapter 2. So today we're going to talk about density. Now, density has to do with the ratio of the mass of an object to the volume of that object. Or a substance, it can also apply to a liquid. So you can see down below here we have the equation for density. Density is equal to mass over volume. Now up above we have a picture of different objects in water, and water has a density of 1 gram per milliliter. Now what's interesting is that ice has a smaller mass to volume ratio. So the density of ice is 0.92 grams per milliliter. And because the mass to volume ratio of ice is smaller than water's mass to volume ratio, ice will actually float in water. So if you've ever wondered why ice floats, it's because it has a smaller density. Now, if we look at other objects in this water, like cork has a density of 0.26 grams per milliliter, so its mass to volume ratio is really, really small. Now, at the bottom of the beaker of water here, we have aluminum with a density of 2.7, which is greater than the density of water, so it actually sinks to the bottom. And then same with lead. Lead's density is 11.3 grams per milliliter. So it is very dense. Now in your textbook, there's a table of densities for common substances, and it's divided up into solids, liquids, and gases. And we'll talk more about solids, liquids, and gases in a later chapter. Now, we already talked about the density of cork. We also looked at aluminum and lead, but you can see that there are some other solids in that list, and their densities are increasing as we go down the list. So we also saw ice, I should point that out. Now, muscle is listed in here, and its density is 1.06 grams per milliliter. So kind of similar to the density of water. Bone has an even higher density of 1.8 grams per milliliter. And then some metals are listed down at the bottom. So for instance, copper has a density of 8.92, silver 10.5, etc. Now, if we look at the liquids, we already talked about water. Water has a density of 1. Oil, or olive oil, has a density of 0.92. So if we were to pour some oil into a glass of water, it would actually form its own layer above the water. So it would float. Gasoline also has a lower density than water of 0.74 grams per milliliter. Let's see, and then if we go down to the bottom of the list, mercury, which is found in thermometers or older thermometers, mercury has a density of 13.6 grams per milliliter, so it is very, very dense. Now, you might have noticed that the units so far have been in grams per milliliter. But for gases, the density is listed as grams per liter for its units. So gases, we'll talk about later, like to fill the containers that they're in or the space that they're in. So gases can actually fill up an entire room, which means their volume, it will be larger naturally. So we tend to use liters to describe volume there instead of milliliters, which is smaller. So if we look at the densities of these different gases, we can see that they can be quite small, but again, we're in grams per liter. And then carbon dioxide at the bottom has the highest density, so that's what we breathe out, and the density of carbon dioxide is 1.96. The density of dry air is 1.29 by comparison. Now you might also know that hydrogen and helium gases are very light, so they tend to float up. So if we look at the densities here, helium and hydrogen have really small densities. So they're very light gases. Okay, so we already talked about how to calculate density. We said that we're comparing the mass of an object to its volume. So we could summarize this as a capital D equals m over v. Now we can also rearrange this equation to solve for, let's say, mass or volume. So let's say we're trying to solve for the volume of something and we're given the density and the mass. Volume would equal mass over density. And then if we wanted to solve for the mass of something, that would be the density times the volume. So we can use this equation in multiple different ways. So on the previous slide, we saw that we can use units of grams per milliliter. But remember, I had also mentioned in a previous lecture that 1 milliliter is equal to 1 centimeter cubed. So we could just as easily write grams per centimeter cubed. Now typically we'll use grams per centimeter cubed for solids, and we'll use grams per milliliter for liquids. But it's okay if you interchange milliliters and centimeters cubed because they equal the same thing. And we also saw that the units for the density of a gas is in grams per liter. Okay. Now, how do we determine the density of a solid, for instance? The density of a solid can be determined by dividing the mass of an object by its volume. So to find the mass, we can use a balance. And here we have an object, and we've placed it in a weigh boat, and then we place that on top of a balance. Now, typically when we're using a balance, what we would do is we would place the weigh boat by itself on the balance, and then we would hit a button that says 0 or tare, and that would set everything to 0, and then we would place the object in the weigh boat and get an accurate mass for the object by itself. Or another way to do this is to weigh the weigh boat by itself, and then weigh the weigh boat with the object in it, and then you can subtract the mass of the weigh boat. But we'll get practice with that later on. Okay, so how do we actually get the volume of this object? Well, we can use something called volume displacement. So what we do is we grab a graduated cylinder, and then we put some water in that graduated cylinder, and we note the initial volume. So in this example, it's 35.5 milliliters. Then we submerge the metal object in the water, and this metal object is zinc. And then we take note of the final volume, so 45 milliliters. So that means the volume increased when we added the object, which makes sense. We're displacing some of the volume of the water. So then what we do is we take the mass of that zinc object and divide it by its displaced volume. Now, to determine the displaced volume, we're going to have to subtract the final volume, the initial volume from the final volume. So we're going to subtract 35.5, the initial volume, from 45.0, the final volume. And that will give us 9.5 milliliters. And then because this is a solid object, we might decide to use centimeters cubed as our unit. Now notice the sig figs. So we're doing subtraction here. So we don't care about the least amount of sig figs. We actually care about how many decimal places we have. So notice that 45.0 ends in the tenths place, and 35.5 also ends in the tenths place. So our final answer should end in the tenths place. Okay, so now we put everything together. So we're going to plug in the mass of zinc, which was 68.6 grams, and we got that from the balance. And then we divide that by the volume, which we just determined was 9.5 centimeters cubed. So now we're doing a division problem, which means we care about the least number of sig figs. So how many sig figs does 68.60 have? 4. So we've got those first 3 digits, which are non-zero digits, and then that last 0 there, that is after a decimal point and a non-zero value. So it is significant. And then how many sig figs does 9.5 have? 2. So that means our final answer should have 2 sig figs. So once we plug this into our calculator, we get an answer of 7.2, which has 2 sig figs. And you might have to round depending on what your calculator gives you. Okay, so let's do a practice problem. What is the density in grams per centimeter cubed of a 48-gram sample of a metal if the level of water in a graduated cylinder rises from 25 milliliters to 33 milliliters after the metal is added? Okay, so we have our initial volume of 25.0 milliliters, and then we put our object in that sample of water, and the volume increases to a final volume of 33 milliliters. All right, so we also have the mass. So if density is equal to mass over volume, we can just plug in those values. So feel free to pause the video and calculate that, and when you unpause, we'll check your answer. Okay, so let's plug in 48.0 grams divided by 33.0 minus 25.0 milliliters. Okay, so we've got 48.0 grams in the numerator. And what is our total volume of the object in the denominator? .0 milliliters. Okay, so now let's do that division. So 48 divided by 8 is 6. And how many sig figs do we need? 2, right? Because 8.0 has 2 sig figs. Okay, so we've got 6 grams per milliliter. And here's the solution slide if you need that later. So now, one last thing. If the volume and density of a sample are known, the mass in grams of the sample can be calculated by using density as a conversion factor. So remember earlier we said that we can rearrange our equation to solve for mass. So that would just be density times volume. And similarly, if the mass and the density are known, the volume can be calculated. So remember that would be mass over density. All right, so let's do a practice problem. Let's say an unknown liquid has a density of 1.32 grams per milliliter. what is the volume of a 14.7 gram sample of the liquid? Okay, so we have a few given things here. Let's write those out. So we're given the mass of the object, or the substance. So that's equal to 14.7 grams. And then we're also given the density, and that is equal to 1.32 grams per milliliter. And what we're trying to find is the volume. Okay, so which equation should we use? So if we go back, we said that volume is equal to mass over density. So let's use that equation. All right, so all we have to do is plug in all of those values that we were given. So let's plug in the mass and the density. Okay, so let's plug this in. I've got my calculator here. 14.7 divided by 1.32. And I get a super long answer here. So I've got 11.13636, etc. Okay, so first of all, let's figure out how many sig figs we should have here. So how many sig figs does 14.7 have? 3. Everything is a non-zero digit. And then what about 1.32? How many sig figs does that have? 3. Everything's a non-zero digit again. Okay, so that means our final answer should also have 3 sig figs. So let's look at our first 3 digits there. And then the next digit is a 3, so we don't have to do any rounding. So our final answer will be 11.1. But what about our units? What's our final unit? So if we look at our units in our equation, grams will cancel. And then we have milliliters in the denominator of a denominator. So that is actually in the numerator. So if you imagine we have 1 over milliliters. So that actually means we have milliliters in the numerator. So our final unit will be milliliters. And that makes sense because milliliters is a volume unit. So we were trying to find volume. It makes sense. Okay. So here are the solution slides for that problem. Oh, I accidentally zoomed in. All right. So we've covered everything that we needed to in Chapter 2. So we covered metric units, and we went over the different types of units that we might see in chemistry. We also talked about significant figures and how to round or how to add zeros to something that needs more sig figs. And we also went over some calculations using sig figs. We also talked about prefixes and how they can be used to change the size of metric units. And we talked about equalities and how to turn those into conversion factors, and then how to apply that to problem solving. And finally, we talked about density. We skipped specific gravity. We're not going to use that in this class, so don't worry about specific gravity. Okay, so I hope that helped, and you do have a lab this week based on density. So you might want to review the section that we just covered for the lab. All right, so I will see you in the next video.